for them, and that's the reason we don't have any multiple choice quiz for this homework, uh, which generally has the deadline of 1 week. Labels are ordered, but they are not time synchronous. I'll explain what this means. Uh, Labels are list of lists. So you while loading them, you'll need to convert them to tensors, um, not numpy arrays. Sorry for that. You'll need to convert them to tensors. Um, must generate this sequence of phonemes. We have 41 phonemes and one blank character. So I'll I really hope that you guys have gone through the homework and you guys have started this. If not, this is the time to start. Please start. This is the phoneme list we have. Um, we have all these phonemes uh, which are there in the audio file of those MEL spectrograms, and this is the phoneme map. Because we cannot use these directly, we have them coded in, I mean, assigned. It's one-to-one assignment. We have assigned them to the uh, all these. So eventually they'll be they'll be processed using the ASCII values of all these characters over here. So this is about it. We have the loss we are going to use in this homework is not the normal scale divergence or anything. We have CTC loss. I think today we had a lecture about CTC loss, right? So that's the one we are going to use over here. The same CTC loss, you're going to write it in homework 3 part 1. We'll go through that in this bootcamp again. But yeah, basically CTC loss, you can install. There's one, I think, Git repository which you can clone, or there's one pip install. I think check the documentation about it. Same thing is there with the Levenstein distance. You can import, edit distance, Levenstein distance from. There are a couple of them available for pip install, or the APIs, or they are there. Just check the documentation for them. Levenstein distance. Do you guys know what Levenstein distance is, or shall I explain it? Please let me know if you guys need the explanation for Levenstein distance. Okay, cool. I'll explain it. Levenstein distance is generally one-to-one distance of between two strings. So if I have, I'm giving an example. If now we can see over here the word distance. If I change two characters in it, and I try to find the distance between those two strings, I'll get the distance 2. It's as simple as that. So we are going to use that as our metric, and the strings which you guys are going to upload on the Kaggle. Kaggle is also going to check the Levenstein distance between the ideal output and your output. And you guys must have been thinking why there is 108. So currently the Kaggle score you must have I hope you guys have submitted the early deadline CSV file over there. So most of them must be 108 something. That's the basic distance which we guys have provided a sample file, and the original the ideal output has. So the cutoffs will be again according to the Levenstein distance for this homework. Okay. In this model, I think we have, in lectures we have gone through one-to-one, many-to-one, and there are a couple of such arrangements like this. I hope you guys can see my cursor, right? So So this model will be many to many, but the point where I said it's not time synchronous is because we do not have the output for every block. Okay. Um, yeah. Okay. We do not have the output for every block. We have the output for how to say. I'll explain which blocks we'll have the output for in the next slides. But just we have it's just because if I say then we do not. So for every 10 milliseconds, if the MEL spectrogram is sampled for every 10 milliseconds, what happens is that particular every sample which has in it will give us the same output. We do not need the repetitive outputs for this. That's the reason we only consider on one output from all of them. It's because of that. Yeah, so we have gone through RNN, then LSTMs, the GRU. What you can use in this homework is whatever you have been learning up until now. You can try. So uh, main thing is we need to capture sequential dependencies. So RNNs, again, we know that RNNs are the best bet for that, and you can use LSTMs or GRUs or even RNNs. We have RNN cells and RNN LSTM GRU, everything in PyTorch. You guys feel free to use any of them. Just please make sure that you guys go through the documentation thoroughly through the documentation. We have it was still okay if we did not do this thing in homework 1 part 2 and homework 2 part 2, because there was, at least we could be sure about we are going to get some error, some or the other error if we don't follow it. But this is something where if you don't check the dimensions, so RNNs, I think they take the length first, batch second, and feature size as the third input. There is one more flag kind of thing we can set, which is batch first. If it is true, then batch goes first, and then length, then feature. So make sure you guys you know what exactly you're writing. The reason I'm talking about this so much is because uh, because if there is no shape error and you think your model is running fine, but your model doesn't think so. In short, you are feeding the different inputs than the ones which are expected. What happens is you are uh, posing a different problem altogether to the network, and the network will also try learning the wrong problem statement than whatever you need, and it will be after a point good at learning the wrong problem statement, and you will see the loss is getting down. It's learning, and you won't get the output which you need. It might plateau super hard at some point of time, or I mean, that's what will happen, and then it will be a little harder to debug. So um, please check the inputs and the sizes, everything properly. The hint for this homework will be, if you guys have gone through the recitation last week, I explained why convolutional layers do help in sequential dependencies. So uh, if you use convolutional layer, it is better at capturing sequential dependencies. So you may use them. You may use any linear layers or the embeddings, whatever you feel like. In here, you may choose your own um, ReLU or any of the other activation function. Uh, the only thing which you need to be attentive with is to not use attention in this homework. We have not covered it yet, but you're not allowed to use attention in this homework specifically. We are going to cover attention in next few classes, and your next homework is totally about the attention. So you'll have a test of it over there. Yeah, the main problem, I won't say a problem, but main thing we are going to do over here is in homework one, if we compare homework 1 and 2 again, the data, uh, the, the the type of the data which we had equal length inputs in homework 1 and homework 2, but in homework 3 we have variable length sequences. So so first, let's say first MEL spectrogram is this long, second might be this long, third might be this long, and so on. So we have this variable length sequences, and PyTorch always needs every input's size should be same. This is what is needed from the PyTorch every time. So the first thing in which may come to our mind is padding. The same thing which we are going to do. Padding means we are just concatenating zeros over here, getting the maximum length, and pad 0 so that we get this squared, let's say rectangular shape, and we get the input size. Same for this. This is the first method we can handle this thing with. Uh, what happens with this is basically if one of the utterance is too long, um, yeah. So there's a question: do we pad each utterance? So we do pad each utterance except for the one which is the longest one. Does that make sense? Yeah. Okay. So this is how it looks. If one of the utterance is too long, then we end up padding these many zeros everywhere, and there are you can see there are more zeros than the data in here. So there's another question. So the longest utterance in the data set becomes the standard. Um, I don't think this is something about the standard. It's just that we need the shape of every utterance, uh, which 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 should be the same, right? So what option do you have other than this? Uh, we don't have any, right? So longest utterance in the dataset or the batch. That's what I was going to talk about in the next point. Uh, so this is the one thing. If we pad in init, which means that we are padding for the whole data. I think that's what the question is about, right? The longest utterance in dataset or batch. If we pad it in init, we end up padding for the whole dataset, and which might end up like this figure. So the whole dataset, one of the other utterance is going to be so long, and we might end up padding whole dataset with all zeros, and that is computationally very intensive while processing it. So we prefer padding them in batches. If you guys have really speedy GPUs, you may go ahead to pad them in. Uh, no, I'm kidding. It's not the efficient way. Second method is pad packing. Pad, pa okay, I'll go through the uh, TS on the call. Please notify me if there are any questions, or else it's a little difficult to monitor chat every time. I'll go ahead. The second method is pad packing. What first we'll understand what is packing now. We have these utterances and they are variable length. So element 0, 1 to 3, let's say these are the utterances. What packing does is it just sorts them in the descending order, and like you can see in the figure, the figure 3, the number of figure is 3 over here, but yeah, it sorts it in the descending order, and it arranges them like this manner. So zeros of all these elements in the stacked first, then all ones, then all twos, and so on. And packing again takes the input of every element, right? So it has the data how to pack and unpack with respect to the length of every utterance. And this helps us to get rid of padding altogether, right? We don't have to pad zeros anywhere, and still we have this rectangular shaped data. This is what we need for giving an input to the PyTorch functions, right? So the only thing is, this function being a PyTorch function, we need it to be uh, padded with zeros. But the difference between only padding and pad pack sequence is, in if you feed packed sequence, PyTorch knows that it is a packed sequence, and it's even if we are even if we are giving the input of padded sequence to the pad packed sequence function, it ignores all the zeros, and it processes with this. So it helps us reducing a small amount of runtime if there are a few longer utterances available in our data set. Since we don't know them, we just use this method generally, uh, considering this is the faster one. These are just the suggestions. If you find anything smarter than this, you're free to use any of those methods. So yeah, uh, we first use. Okay, there's a question. So we padding each batch first and then use packing, or we just do packing? Uh, we do pad first. It's because you can see the function over here, right? Pack padded sequence. The name of function is pack padded sequence is because it's a PyTorch function and it cannot process the variable length input. So we pad it first and then pack it. The difference in over here is the zeros are ignored and they are not processed, which saves us the runtime. Does that clear? Okay. Um, so we do pad first. You may choose to pad in the collate function itself. I'll talk about the collate function. Okay. So we do pad first, then we give that padded squarish rectangular-ish input to the pack padded sequence, and it packs the whole batch. So um, we are again creating the batches in our collate function. So it packs the whole batch of the padded sequence, and it requires sequences and sequence lengths as well. The reason we discussed before, it needs to unpack later and it needs the lengths to unpack. So the lengths are pretty important in they are going to be important in every step over here. And while unpacking, the function name is pad pack sequence. So you get the output of x and x lengths. X is again the batch. X lengths is the out lengths of every utterances in that particular batch. It unpacks back to the batch of padded sequence, and this is how the output is gonna look like. Collate function. We are we did not use a specific collect function up until now. So I think the latest we talked about the collect function was in homework 0, if I'm not wrong. But now we are going to use the collect function is because, uh, I mean, it's again a design choice. If you don't want to use the collect function and uh, you want to do something else, you may feel free to, but this is again the easiest way I can think of. Yeah, I don't think there's any other way to get the padded sequence in the data loader. Yeah, so I think you're going to use the collect function in this homework. It's just because while making the batches, we need the batches to be padded, right? So a collect function, uh, again assuming what is, you guys know what is the collect function. Shall I assume that, or I forgot? Okay, I'll explain it. Collect function is uh, used. This is out of the scope of this homework. I'm telling you that collect function is generally used to create the batches. Now, up until now, we were just using the init and get item functions generally before this homework to um, to pro, to pre-process the data. But in the data loader, how do you guys think the patches were being made in a way that you're using it again in the later part of your code? Your data loader function itself creates the patches for you, but if you write a collect function, let's say some random collect function of your own, and there is a way that you can give that collect function as an input to your data loader, so that it's generally you are telling your data loader function, I'm sorry, you're telling your data loader function to uh, use my own collect function, do not use the default one. That's all it is. So collect function can be used for any processing you want. In here in this homework, we need that collect function to uh, pack sorry, pad the sequences, pad the batches. That's the reason we are going to use the collect function over here. Yeah, now uh, as I was telling you, this, let's say there were, uh, this is wrong. The B should have been over here, but basically, if there is a utterance of B up until here, we have the output of B, then AH, we have the output of AH over here, and again T. So this is how our output is going to look like, but generally we get the output for every uh, what to say, every instance, right? Every 10 milliseconds of spectrogram will have some output. What happens that is we just accumulate the everything to have this specific, this one output. That's what the RNNs are for, right? So we are going to use them in this way. We uh, Up until now, what used to happen was we used to get the probability distribution of the classes, and we were just argmaxing them to get the class which, in short, the class which had the highest probability. We used to choose them, right? Now in this homework, that is not sufficient. We have sequential dependencies, as we talked about. That's the reason we need, what we are going to get as an output is probability distribution of sequences. Now these probability, we are going to get probability distribution at each time step, but we need the highest probability of not that particular time instant. We need the highest probability distribution of the whole sequence. So uh, I'm not sure if have we covered beam search in the lectures yet. If not, the one of the upcoming lectures you are going to see what beam search is. But um, let's see. I'll try to explain you what the basic idea about this is. So we have some sequence A, B, C as an output, let's say. So up until now, what we were doing was we used to get the probability of whole thing as a probability of class, and we just used to use them as an output. Now, because this is a sequence, uh, we are going to get the probability of this with uh, which has the dependency of this probability of A again, and C will have the dependency of probability of B and C, if that makes sense. If it doesn't, please do not uh, think about it. A professor is definitely, he is going to explain better than me. But uh, what beam search does is, if we have three different sequences A, B, F, and A, B, M, let's say, it is going to calculate the probability of all these, I mean, all the sequences which are available, and it is going to prune out the lower probabilities one by one, and the one which is still there, which will be there, as in the which anyways going to have the highest probability, right? So um, that is going to be selected, which is in short the gist of a beam search. Greedy search is nothing but you are just directly going to get you, if you see the probability of A is highest, you are going for A. If B is highest, you are going for B. But then this might create some issues if we we extend the sequences from here, and the sequence goes wrong from that point. So uh, that's the reason beam search is useful. Now in this, one second. Um, in this, there are two different things. One is training phase and one is inference phase. Training phase, we are using greedy search. Greedy search we are using, it's the reason behind that is we have the ground truth, right? We have the labels for a training set. So we have the labels for validation set as well. So we can leverage our greedy search to you we because we anyways have the loss to back propagate, and we know that if it is going wrong, we can correct it in the next epoch. But in the inference phase we do not have that, so we need to have a different there's one more step we need to implement, which is a beam search. um, I wanted to ask if whatever I'm talking is making any sense to you guys. I did not have any response up until now. Please feel free to ask questions. I'll stop here to take some questions. Yeah, cool. I'm taking one answer as a collective feedback from you guys, and I'll move ahead. So, yeah, you guys are going to write beam search decoder as well. So you may use your own from homework 3 part 1 if you want. That is fun again. So I'll move to the next slide. Advice for this homework would be, please watch lectures and recitations and this boot camp. Please do watch. I know you guys who are watching, you generally watch everything, but um, there are some students who might think that it may be the waste of time. But for this homework, please to watch everything which is being covered and which is going to be there in this homework is covered in the lectures and recitation. So I urge you to watch all of them, read the entire write-up, understand the problem before you are starting, and please know whatever you are writing, because if it, as I told before, if it goes wrong and still training, you won't understand, and you won't understand what why I'm not getting the results others are getting. So please make sure that you guys know the shapes, you guys know what you guys are writing. Look at the submission example. So I'll tell you my own mistake in this homework. Uh, there must there must be I must be the only one who can make such a stupid mistake. But what I did was I submitted the file with some uh, some ABCD. Let's say ABCD was the expected output. I submitted this with there is one space over here and over here. I submitted it with this the function I was using to make a string was giving me the output in this particular format, and the expected output for this was ABCD, let's say. So whatever result I was getting was the actual Levenstein distance of my own code was plus that plus 4. So these 1, 2, 3, 4, these characters were getting added as a distance to my own. So there can be such mistakes. Make sure that you go through the files, everything, and make sure that what you're doing, it's correct. Um, Check the tensor shapes again, whatever I was talking about. Uh, Use whatever you have learned from the previous homeworks. Uh, and this home this homework, you are going to be patient with your model, because this this might happen in this homework that there are 20 epochs and loss your Levenstein distance has not moved by a lot margin. So this may happen in this homework, and still it will reduce after that, after 20 epochs. So you might uh, think of the patients, what you're going to be uh, using over here. Um, I'll I think these are some helpful references. You may go through them. I'll upload this on the website, and I'll stop for the questions now. What is the estimated time it will take to train the models? Is it similar to ResNets? Um, so it was a little bit different about ResNets, but just if you are considering the time to train the ResNet and time to train this uh, one epoch for this should be similar. But again, depends upon how many layers of LSTMs GRUs you're using, what exactly you're using. If you're using Are you using in the single direction or bidirectional LSTMs? Which activation function you are using? How many layers of CNNs you are using if you are using CNNs? How many layers of embeddings you are using if you are using them? It's all again depends upon the design choices by you guys. So again, we have released the toy dataset. You may use it for uh, checking if your model is running or not, and make sure you use all the resources, and I wish you guys all the best for this homework. If there are no more questions, we'll move ahead to the reference code for this. I am assuming there are no more questions. I'll be available on chat. uh, Sheila, I'm stop presenting now. I'll stop presenting now. Sheila will take over. And
Okay, hi everyone. If anyone has a question, just post it in the chat, and one of the TAs will alert me. Okay, can you all see my screen?
Yes, I can.
Okay. So I'm just going to go through the starter notebook and put most of the things that Ojas just covered in context for you to understand how you're going to actually implement them in code. So I'll just skip these first two steps because they're just basic bookkeeping to ensure we've connected to Google Drive and we're able to download our data from Kaggle. So I just mentioned two important libraries that you need to use for this homework. One is CTC decode, and and the other one is any library that can help you to compute Levenstein's distance. So this is the code from the README of the CTC decode library. You can use this to install it, and this will help you when performing beam search. And then this other library will help you when you're computing your Levenstein distance. And then after that, it's just basic library imports and setting some important variables such as our device, because you want to be training on GPU. And then this is just a normal data loading that you've been doing in the previous homeworks. We have our dataset class, but now, as I just mentioned, this time things are going to be different. We're going to use a collate function to do some pre-processing, because our data is of variable length, and PyTorch expects data to be of the same length for it to be able to compute. So I just mentioned using pad sequence. So this is where you should ideally be padding your input data, so that the padding size can be the size of the longest length of your data. So this is where you will write logic to do that, and you can use the pad sequence function. It's a Python function, if I'm not wrong, it's in the utils package. So I just chose to separate the two dataset classes. This is for the training and validation data, and this will be for your testing data. But you can just also have them as one function and programmatically check whether you're looking at the testing data or the training or validation data. So after that, here, this is where you are going to be using your collate function. I chose to have it in the dataset class, but you can just have it as a separate function and refer back to homework 0 if you're confused about any of that. So maybe if there's any question on the chat, I can answer it now before I move forward. So it seems there's no questions, I'll just proceed. So that was the first section where we are handling the variability in length of our data. Now I'll go to the model creation phase. Here we intentionally didn't give you any starter code because we want you to experiment. So I just had mentioned you can use embeddings, or even you can use a CNN for you to be able to extract features that your LSTM will be using in training. So you can try all these things here. And as he had mentioned, you can decide to use RNN, GRU, LSTM. It can be bidirectional if you want. So just play around with everything here. And then if you're using LSTM, in the forward pass, this is where you'll be packing the padded sequence as well as unpacking it. So this is where you'll ideally be performing that logic. So I'm done with that. This is just how you'll be initializing your model. If you're using CNN, you might decide to have parameters like kernel size, among other things. And then, so we just already mentioned that we're going to be using CTC loss for this homework, and PyTorch already has it, so you can just import it and use it. You can use any optimizer. It can be a hyperparameter that will be tuning. You can use SGD, Adam, or whichever one that you want. And as always, we always advise you to use a learning rate scheduler. So you can just choose the one that you want. And in your training epoch, the logic will be very similar to what you had in homework 1. The major difference is you'll now be using CTC loss. I'll advise you to go look at the CTC loss documentation, the official documentation, for you to understand what parameters it's expecting on your end. So that's the training phase. And then now we'll need to validate our model. So there's a file that we've given you, phoneme list, and it contains a phoneme map because that is the expected output. So this is where I have imported the file for you. And then I've called the CTC decoder library for you. And just something important to keep in mind, if you want to perform greedy search, you can still use the CTC beam decoder library. It has a parameter called beam width. So just pass a width of 1, and then it's going to be performing greedy search. If it's greater than 1, now that will be beam search. So this is important because having a higher beam width increases the time that's going to be taken in processing your output. So when you're validating your model, it's advisable for you to perform greedy search where your beam width is 1 because it's going to be faster. And then now when you're actually generating the actual test output, you can use a greater beam width because it's going to improve your accuracy. So similar to what I had in the testing model, the logic will still be similar. Remember, we're using CTC decode, but now, we're using CTC loss, but now an important thing is, because we want to actually evaluate our model, we'll need to decode our output. So we'll just use the CTC beam decoder, decode our output, and by decoding, I mean getting the phoneme maps and now computing the Levenstein distance between what you get and the actual expected output that you've been given in your validation set. And this will give you a hint of how accurate your model is. Then after that, this is just the normal loop that we usually have when you're training your epochs. It's always advisable to save your best model. So there's provision to do that here. And I'm done with the actual bit where we had starter code, and now from there you can just have code to test your data, make predictions, and then submit your predictions to Kaggle. And remember, use the CTC beam decoder library to perform beam search and actually get your phoneme maps. Yeah, so that's it, unless there's a question that I need to address. I'm assuming everything was clear. If that's the case, then I'll just hand it over to the part 1 team. Just one thing, so the notebook is already on the website, so you can just download it there.
Okay. Yeah, I think we can get started with part 1. So Zilia and I are going to briefly go over what to expect for homework 3 part 1. So you're expected to implement RNN, GRU, CTC, and search. Okay, so first for the RNN section, you need to implement a single RNN cell. And as you can see here, we have already given you a equation for the forward pass for the RNN. And you do have to implement calculate the gradient for the backward pass yourself. So implement these equation in the forward pass and then implement the backward pass using the gradient that you calculate yourself. And after we have this RNN cell, the next task is to implement this phoneme classifier with the RNN cell that we just implemented. So this task is basically implement a classifier with the input as a sequence. As a sequence. So as you can see here, x1, x2, and x3. So the graph on the left is the forward pass, and on the right is the backward pass. Basically, you're just having two loops. We first loop through this sequence, and the inner loop would be each RNN cell here. And then moving on to the next section, which is GRU. The section has a really similar structure with RNN. So similarly, you need to implement the forward pass for GRU cell. The equations has already been given here. And then you need to calculate all the intermediate gradients that's going to be used in the backward pass. You can see here it's pretty complicated. We have a lot of weights here that needs to be calculated. So we do recommend you to graph a computational graph yourself. And if you're unsure about this link provides a really useful tutorial on how to draw out computational graphs and calculate gradients. So definitely visit this. And then after we have the GRU cell, we need to again implement a inference model. This is much simpler than compared with the RNN classifier. Here we only have one GRU cell and we pass it through a linear layer. And we only need you to do the inference. So there's no backward pass and only forward function needs to be implemented. So I'll quickly show you what the code looks like. So this is the file structure of homework 3P1. It should look like this when you download the handout from the AutoLab, and you don't need to add any additional files to this. And first, we need to implement the RNN cell here. So basically the forward function and then the backward function. Yeah, and after we have the RNN cell, implement the RNN classifier in RNN classifier.py. As you can see here, we have already given you the initialized code for the model. So make sure you understand these code and then uncomment this. And we also gives you some really high-level pseudocode for the forward and backward pass. So definitely read those before you go ahead and implement the forward and backward pass. And then we have the GRU cell. Yeah, similarly implement the forward and backward function. As you can see here, we have a lot of weights for the GRU cell. So definitely start early because it's going to be complicated. And finally, for GRU inference, so this self.rnn is basically this GRU cell here, and then the projection refers to the linear layer. And then since we only do inference, there's only the forward pass, and then we do the actual inference here. So make sure that you call the forward function for this character predictor here. And so the autograder should be similar. All you have to do is call the runner inside the autograder file. So, sorry. Yeah, and this would run the whole autograder. And if you want to run individual tests for each section, you just have to add a argument at the end. So for example, MCQ, it will run only the multiple choice questions. And then for example, like RNN, it will only run the test cases for the RNN section. And we do provide you with a toy runner, which basically runs your code on a much smaller test cases. So if you call the toy runner and then add the section name behind, it will run a RNN toy runner for you. And as you can see here, we print out all the input values and hidden values for you. And right now it's raising not implemented error, but if you implemented the function and you got a wrong value, it will also show you what to expect for the test cases. And you're also welcome to check out this toy problem file. So you can add some additional print statement in this file to check any intermediate values you want. Yeah, and that's basically section RNN and GRU, and then Zillian is going to go over CTC and search. Okay.
Okay, thanks, Abby. Can you see my screen now?
Yeah, I can see.
Okay, so there are two more sections for the homework 3 P1. One is about the CTC and the CTC loss, and another part is about the searching. So basically the greedy search and also the beam search. So for CTC and CTC loss, there are two files you need to implement there under MyTorch. The first one is ctc.py. So under this file, you need to implement 4 functions, and these are 4 functions, and I recommend you to implement them in order. So because like as long as you implement them in order, you can get scores. Otherwise, you cannot just jump around. So I think like for CTC, so for them, like Big Shot covered most knowledge about this part in today's lecture. So I just copy pasted the pseudocodes from the lecture. And what you need to do is to understand what he was saying in the class, and also to understand what this pseudocode is doing, and you try to implement them in your code. And one thing to notice is that here the index is from 1 to n, and in the code you have to index from 0. So that's the only differences from the pseudocodes to your codes. So apart from that, I think everything is the same, even though for the input arguments and also the output, they're basically the same. So this is the forward algorithms. This is corresponding to the forward probability function. And also this is the backward algorithm. And in the end, you want to put them together into your computing posterior. Here you get your gamma and also use your alpha and beta, calculate from your forward and backward. So this is for the CTC part. And yeah, and also you have to implement the derivatives of the CTC. Here, these are pseudocodes for that, so you just need to refer to the lectures. Another file we want to implement is a CTC loss. So this is also under MyTorch. And here there are 2 functions, forward and backwards. I think for the forward, there's a for loop and already written down in the file. So it's a for loop over the batch. And inside the batch, we already provide the comments about how to proceed this forward. So you need to truncate your target and also need to truncate your logits. This target and the logits are the input arguments. And after that, you can call your function extended target sequence with blank from your CTC file here. Yeah, the first function, and just call it. And then you compute the forward probabilities, compute backward probabilities, and then compute posteriors. And then in the end, you have to write some codes, piece of code to compute the expected divergence and store it in the total loss. And I think above this for loop, there's a note saying attention, you have to get the mean of your loss, and that's your total loss. So remember to use the average loss. So yeah, so that's for the forward for CTC loss. And for the backwards, also there's a for loop over the batch. And the procedure is you need to do the same thing, truncate your target, truncate your logits, and also extend the sequence with blank. And then you call your function, compute the derivatives of the divergence, and then store them in the dy and return the dy. Yeah, so basically for this CTC loss, you just call your function, you implement it in your CTC. So it should be fine. Yeah. So another part is about the beam search. So for beam search, it's under MyTorch search, and there are 2 functions. One is greedy search and another is beam search. So for greedy search, that means you just need to get the symbol with the maximum probabilities and put them as your forward pass, and give it and also output your forward probabilities. And for beam search, I think this big shot will cover it in the next lecture. So please first attend the class and watch the lectures, and then implement your homework. So for beam search, also here is the pseudocode from the lecture. I just copy paste here and for reference, and you can see there are this is a main framework, and there are several small functions. For example, initial pass, prone, extend with blank, and extend with symbol, and merge identical passes. So these are some extra functions you can implement separately. So here are the codes for all of them. Big Shot will cover them. So if you cannot understand what are they talking about here, so just wait for next lecture. And I think that's all for the searching. And also for CTC and the searching part, we have the toy problem. So after you implement each of them, you can first try with the toy problem. And if you pass it, and try to the main autograder. Yeah, so I think that's it. So any questions? Basic question, why are we using beam search? Oh, so for greedy search, because you just get one pass in the end, but that could not be the or technically not the best pass. So you need some potential candidates during the searching. In the end, you find the best one from these candidates. Yeah, that's not the best answer, but if there's no other questions, so I think that's the end of today's bootcamp.
Yeah. I think we can hang around for 5 minutes or so. But if you have no further questions, feel free to leave.
Yeah, thanks for coming.